The most efficient way to do nothing is to do nothing. Actually, the full quote is, the most energy efficient way to do nothing is to do nothing. But it's my professional opinion that all great quotes are misquoted. Now, I've already made a video that's all about power efficiency. That video was all about using big, complex instructions to do a lot of work efficiently. But by doing nothing more efficiently, we were able to reduce power draw in RPCS3, in Ninja Gaiden by 4 watts, in Demon Souls by 4 watts, and in Nier by 5 watts. Now, it actually took many iterations for RPCS3 to get to the point where it can now do nothing efficiently. Here's the most basic do-nothing code that you can have. Here the CPU will simply check if the value true is true in a loop forever.
True, and yeah, that's pretty true. That's true, and yeah, that's true. That's true. That's true. That's pretty true. That's pretty true. I mean, that's true.
Now that's not really so useful. But what if instead we wanted to do nothing for a specified amount of time? For instance, let's say we put something in the oven, and we want to check in on it in 20 minutes. We could use this code, but it's going to be checking if 20 minutes is elapsed billions of times per second for 20 minutes straight. What a waste. Imagine if your smartphone started draining its battery every time you set an alarm. Now there are actually a multitude of ways to reduce power when writing this kind of code. Let's start with the most naive power saving techniques. One thing we can do to make this code more efficient is to insert this pause intrinsic. This causes the compiler to emit the pause instruction, which quite literally causes the CPU to do nothing for a number of clock cycles. How long the CPU does nothing is up to the implementation, but it generally waits for less than 100 cycles. Actually, on my machine you can configure how many cycles this instruction waits for in the BIOS. Go figure. Now, the simplest infinite loop draws 3.8 watts on a single core, using this loop. But by inserting pause in there, we cut power draw down to just 1.6 watts. That's more than twice as efficient. But we're still drawing way too much power. Now there is a better way to wait efficiently, but we're going to need the operating system to help us. This code here is how we can tell Windows to let our core sleep for 500 microseconds at a time. This infinite loop draws just 0.8 watts since it's only checking if true is true 2,000 times a second. The most basic infinite loop was checking if true is true 5 billion times a second, while the loop with pause checks about 100 million times a second. That's a nice improvement, but when the cores are truly idle, they draw below 0.1 watt each. Now, why exactly is this pertinent? Why would we want to do nothing? Why does any of this matter? Enter the PlayStation 3 version of Nier. This game has a thread that tells the PlayStation 3 operating system to sleep this thread for 1 microsecond over and over. This is a problem since if we naively ask the Windows thread to sleep for 1 microsecond, we'll end up sleeping for 500 microseconds instead. This option in RPCS3 allows us to change this behavior. The as host setting will simply forward the requested time to the native operating system sleep or wait functions. The microsleep only option will accurately replicate PlayStation 3 microsleep behavior at the cost of some power, but conversely provide better performance in some games. On Linux we can actually set the timer precision to be much higher, to around 10 microseconds of precision, which means that only games like Nier, which wait for a single microsecond, need to have their microsleeps handled outside of the operating system. But we have a number of tricks to make the accurate microsleep implementation as performant as possible on Windows. First of all, when we're waiting, we're actually calling yield in a loop like this. Yield tells the operating system to try and run another thread instead. If there aren't any other threads that need to run, it returns execution back to our thread. This ensures that the microsleep emulation doesn't starve out other threads on machines with low core counts. The PlayStation 3 has 8 hardware threads available to games, so this is important for devices like the Steam Deck. Before we learn how RPCS3 essentially solves this issue on modern machines, let's first learn how x86 operating systems set the cores into a low power mode, and why Windows is limited to a 500 microsecond resolution. When you're sleeping threads on Linux or Windows, the hardware sets up a timer that will fire after a certain amount of time. On modern machines this is the APIC timer. After the timer is set up, the machine executes the halt instruction, which will cause the machine to literally do nothing until the timer fires, or another interrupt wakes the core up. It should go without saying that having the timer fire at a higher resolution will cause the core to wake up more often and consume more power. Microsoft has arbitrarily set this limit to 500 microseconds, so that programmers don't blow up power usage. However, the alternative in most cases ends up burning more power. This limitation impacts more than just RPCS3. Check out this recent post in the Dolphin emulators blog from this June. The developers wanted to create a more accurate frame limiter, and the conclusion they reached was to busy wait for the last millisecond. And yeah, just like RPCS3, they wait 95% of the way with power-efficient operating system functions, and then busy wait the last little bit by yielding the thread in a loop. This isn't even something that's limited to emulators though. This is really something that impacts any game with a frame limiter on Windows. Whenever you're writing a frame limiter, you'll need to consider trade-offs between power usage and accuracy. Maybe Windows 12 will fix all this nonsense. Here's the good news though. While instructions like halt are only usable by the operating system, Intel and AMD added instructions that allow you to wait on a timer in a power-efficient manner in user space. The bad news? This is one instance where Intel and AMD don't implement the same instructions. First, let's explain the instructions monitor and wait. These instructions take a memory address and wait in a power-efficient manner until something writes to the cache line that holds that address. Pretty sweet, but these instructions are only able to be used by the operating system. Well, both AMD and Intel set out to fix this. First, AMD implemented monitor X and wait X. These instructions work just like monitor and wait, but they're usable in user space. More importantly for us, they also include a feature where you can specify a timeout in TSC clocks, and the machine will essentially sleep until that time has elapsed. Perfect! A user space sleep instruction. Only problem is, you need to know how fast the TSC clock is ticking, which differs per CPU. Operating systems don't provide a way to discover the TSC clock, so you essentially have to calibrate it yourself. Oh yeah, and when implementing this, you need to make sure that you set it up such that it monitors an address that won't be written to, if you want to use it as a user space sleep, that is. Now, Intel, rather than implementing these instructions, decided to make their own incompatible version. Intel implemented the wait package instructions, which include umonitor, umwait, and tpause. Umonitor and umwait are very similar to monitor X and wait X. They both work in user space and have a timeout feature. However, rather than timing out after a given number of TSC clocks have passed, it waits until the TSC passes an expected value. In practice, this means that you need to read the clock, add how much time you want to wait to that value, then pass that value back into the expected register. A trivial but silly difference. Now, Intel also implemented the tpause instruction. This instruction waits on a timeout just as umonitor and umwait do, but without the feature of waiting on a cache line, which makes it a little bit more optimal for the use case of implementing a user mode sleep. On AMD, these instructions are supported as far back as their Excavator CPUs, from 2015. On Intel, the wait package instructions were implemented in 2021, starting with their 12th generation CPUs. Do you remember those power efficiency figures from the start of the video? Those were comparing power usage with and without the monitor X wait X pattern on my AMD 7800 X3D machine. On Intel with tpause, the gains in power efficiency were very similar. I wrote this code without an Intel machine of my own to test it on. Don't let it scare you, the gains can be brilliant. You know what else is brilliant? This video's sponsor. Brilliant has thousands of interactive lessons spanning subjects across math, science, data, AI, and programming. Brilliant makes it easy to learn complex subjects with bite-sized lessons that you can tackle daily on your phone or computer. Personally, I've been using Brilliant to refamiliarize myself with calculus, as I haven't touched it since I was in high school. Brilliant's interactive and visual lessons make learning complex subjects like calculus more intuitive. If you're interested and want to start learning for free, go to brilliant.org/whatcookie, scan the QR code on screen, or click on the link in the description. While Brilliant may be a pretty efficient way to learn something, I've actually been pretty efficient at doing nothing on Twitter too. See, my first post was in 2012 asking Hideki Kamiya if he would add 120Hz mode to Bayonetta. And my next post was responding to Tom Forsyth, who was wondering if I was on Twitter after I made this little video. Let's break that streak. Anyways, like and subscribe if you liked the video. Maybe check out this other video that talks about power efficiency. See ya!